to be three-dimensional that we draw pretty much. So the standard 3D coordinate system that I'll tend to use will always be the same, but will often be oriented this way. This would be sort of your standard three-dimensional coordinate system that they refer to as a right-handed coordinate system. Right-handed, kind of a weird explanation for it, but because you got to imagine this first of all as like the inside corner of a room. Okay. If I didn't put the arrows on it, like a lot of people, if I ask, is that the inside corner of something or an outside corner, you get different responses from different people. Okay. How many of you see that as an inside corner, like the corner of a room in the bottom? It's like at least half of you. How many see of it as sort of like the outside corner, of like the corner of this book in an outside sense? Yeah, a few of you. Or some of you sort of flip-flopping between. Yeah, it's like, oh, I see it one way, oh, I see it the other, oh, it's back to the other way. Yeah, that's an issue with these things. In math, in at least this class in Math 228, we want to take this as an inside corner kind of view. Right? So you got to sort of train your eye to see it as like the inside corner of a room. So back to this right-hand coordinate system business. If you take your right hand, there's two ways of saying it. One way is to say if you aim your fingers in the direction of X, you go in alphabetical order, and curl them in the direction of Y, then the thumb points in Z. And because I'm using my right hand, that therefore is a right-handed coordinate system. The other way of doing it is to have your index finger be X, your middle finger be Y, and hold it in a right-handed sort of coordinate system way, and then your thumb is Z. You can then put it any orientation you want. It's still a right-handed coordinate system as long as that's X, this is Y, and that's Z for orientation. This is the standard orientation, though. Putting the Z up as like a dependent variable, right, depending on X and Y. Just the usual way of doing things. All right, so for what I'm trying to explain to you, though, what we could have basically objects oriented around either this x-axis, out the y-axis, or up the z-axis. I'm going to try to give you an image coming out along the x-axis. If I had, I'm going to start not touching the axis, but kind of come out around, and then come back to it as though I was passing underneath there. If this then works its way back, works its way back, in some way finishes off back in here. Okay. Probably I should have shoved that around the back side also. This shape doesn't matter what you put in here, just trying to make it come as though this axis is maybe, say, piercing the surface, say here, and put a little cross on it where you kind of make it look like it's even with that front face. The question is, basically what is the total volume, right? And the way we want to think about getting the total volume is, in this case with the orientation that I have, think of slicing perpendicular to that x-axis. Now I'm not going to try to draw a lot of slices. Let me just take and just kind of extend back just a little bit following this shape of the curve here. Maybe I should have drawn it out a little bit. But, in other words, trying to make this look like I have an object that maybe looks something like this, but has some thickness to it. Okay. I don't know if that really looks the same or not, but I'm trying to say one slice might look like this. Okay. The idea that we want is to try to be able, for all slices in this object, come up with a description as to its area but because it's going to depend on where I am in x, this area would be a function of the x variable for the way I've drawn this one. We imagine the thickness of our slice, right, as being either a delta x, or if you want to think in terms of having already taken the limit, you can certainly write it as a dx. Right, and then, if I did have a whole bunch of slices, from some starting point to the end point, right, the idea would be then that, how do I answer this, what is the total volume? Well, in the discrete sense, I have what? To add up a bunch of these a of x's, times delta x's. But, when I take the limit and think of the slices as being real thin and having infinitely many slices instead, right, this ends up being some kind of an integral, right, of an a of x dx. And, whatever you want to think of as being the limits in here. Maybe it starts at A and goes to B, then this would go from A to B, right, to add up all those slices. All right, so this being the volume, right, and this being the general notion of a cross-sectional area times a thickness gives me a little differential, that's a little differential volume. This guy here. All right, so that's the basic notion. We want to slice things up in all sorts of ways. I'm going to start with some simple objects. The first one I want to do is a cone. You probably already know the expression for the volume of a cone. Let's see. So volume of a cone with radius. I'm going to call the radius big R, and height big H. Right? So that little r and little h are then variable names as opposed to values. So it's a value of big R and a value of big H. All right, so I'm picturing what? Just a cone, something like this. All right, with some kind of a height measure in here. Perpendicular height h, right, and some radial measure big R. I was talking about slicing it. Well, how many ways can I slice it? There's lots of possibilities here. When I'm drawing this cone, I'm trying to give myself a feeling for the shape of it in the background using dotted lines. Sometimes I go a little too far maybe with those. But it does give you the feeling of that circular base. And if I wanted to, I could give myself, say, an orientation in here. You could kind of put this into an X, Y, Z sort of coordinate frame, right, just simply by throwing the axes in. Some people would get fancy and make these dotted inside here because it's kind of within the object if you want to get a little fancy about it. But, if I, for instance, sliced perpendicular to this y-axis through this object, I might see a slice that ran across the bottom in here. Right? And then in some manner, I'm not sure exactly how this can be drawn, but it's going to kind of go up like this and come back down in the same manner. Like that, the slice. I'm not sure if I'm getting the right angles here.
Go up to the side one.
Well, I'm trying to have it not go up to the peak and try to, visually I guess maybe should be shifted over into there someplace.
Well, like the outside of the shell. There.
Right, it's on the outer edge of this thing. So it's a little bit hard to show it around back there. But the idea would be at least that what I'd expect in that kind of slicing, I'd expect triangular pieces that have some thickness. Right? And you could get slices like that. If I slice parallel to y or parallel to x, I tend to get triangular slices. else could I do? I could slice, I guess, what, parallel to the XY plane. That would be more of the sort of typical for a calculus approach. Right? So if I imagine a cone, and what if I'm slicing this way, then what each slice would kind of look like a sort of like what people call a disc, right? Where it crosses through. So you can get disc type slices. Here we have what a triangular. Obviously a circle. This would be, I guess the way I've drawn this, this would have some sort of a delta y kind of thickness, or dy thickness. This one would be some kind of delta z or dz, right? Way of slicing. We will do a little bit of this, not right away, but you can slice kind of in really different sort of fashions. I'm about to draw is going to be a radial slice. So, like for instance, if I came out across here and out here, and this slice would run up. I mean, this kind of thing ain't bad. And then, I realized that if I have some height, and I have a radius, I've got what pi r squared times h is the volume. This kind of thing ain't bad. If you have a base and you have a height, you've got a half base height times whatever delta y or whatever you want to call the thickness, works. Here, if I want to talk about what's the typical volume in here, you've got certainly a triangular shape in here, but then you've got a triangular base, we'll work on it. There's a lot more to that one than some of these other choices. And, when you think about the first two that I did, where you have a triangular slice by slicing parallel to x or parallel to y, versus the circular slices by running up the z-axis. Here to get the dimensions of how big is the base, how big is the height, that's pretty hard because you're working from kind of the front side to the back side of a circle, so you're probably going to be involved with like the square root of an x squared minus r squared kind of a thing, equations of circles, upper half and lower half. And then how high is this, where it meets this center on the edges. It's, again, pretty hard to figure out the dimensions. Kind of like the one down there. It's like not as straightforward as you might see in this kind of a one. So this is obviously the way we're going to take off on this. A lot of folks in calculus don't bother really showing you other possibilities, but I think it's important to consider other possibilities, not only because you might find something that's easier to do, but at this point because I want to make damn sure you're visualizing what I'm saying, that you really see that should be a triangle if I slice that way, even if I'm not drawing it very well. That you really see it should be a round circular disc in the second, and that it should be some kind of weird combination of triangles in the third. And a lot of people get concerned about, you drew this as a disc, but isn't this on a slant? Well, yeah, in the picture it's on a slant, but we're always taking the limit as that shrinks down to 0. So whether it's straight up and down or on a slant or curved or whatever, it's all going to come out to be the same, right? Well, that's that magic of the integral. Taking care of all of that. All right, so let's then kind of back up and start with sort of the usual approach then to this problem, and we'll also work on a pyramid in a similar sort of fashion.